So hello guys, we are saying this is this is our second example to these methods of differential equation. So we are saying we have this differential equation. It has been differentiated with respect to x, and then this other side it has been differentiated with respect to y. Now this just we had a potential function that we have already used implicit differentiation. Okay, so we have already used implicit differentiation to get at this point. Now what method can we use to get back to our potential function, maybe f of x y equal constant c? So this is our exact differential method. We are saying if we have m of xy dx plus n of xy dx equals 0, it's exact. Okay, so we are saying the derivative of m with respect to y should equal the derivative of n with respect to y. So this is Alexis-Cloud's theorem for mixed partial derivatives. Now we are saying our first step is to check for exactness. So how will we check for exactness? We are saying let's perform delta m with respect to y should get delta n with respect to x. Now we are saying our m of x y should equal it's x to the third 3y squared plus cosine of x. Then we are saying our n of x y is the same as 6xy plus 2. Now let's get our delta m. So we're saying delta m with respect to y should give me, now having this, I'm saying I'll do the derivative of m with respect to y. Where there is an x term in the equation, I'll treat it as a constant. So this will go to a constant. So if I differentiate a constant, should equal 0. Then for this case, I'm getting 6y. Okay, now let's continue. And again, for cos of x, it's in terms of x, so it should go to a constant. Now if I take my delta n with respect to y, with respect to x, okay, I'm saying where there is a y, I'll treat it as a constant. Okay, now for this case, I'll have 6y as a constant. Okay, then I'll differentiate this x should equal to 1, so I'll multiply that by 1, same as 6y. Then plus 2, it's a constant, should go to y. Now we are seeing 6y equal 6y, so this statement is true. So this differential equation, it's exact. Now once we have already found the differential equation is exact, so how will we perform to get our potential function? We are saying do a small multiplication at this side. We are saying delta m with respect to y, it's the same as delta n with respect to x. So this is Alexis-Cloud's theorem. Now let's do a cross multiplication at that point. Then we'll get delta m delta x, then use our separating comma. Now we're saying delta n delta y. Now taking the derivative of both sides, so I'm saying take the derivative of this and then take the derivative of this. Now I'm saying the derivative of m dx is the same as the derivative of, now what was our m? We're saying our m was 4x cubed plus 3, it is 4x cubed plus 3y squared plus cosine of x. Okay, now it should be dx. Now we are saying we're integrating this function with respect to x. So where there is a y term, we'll treat that as a constant. Okay, now we are saying how will we integrate this? So we'll get our answer as, at this point now, if we integrate this, we are saying it's 4 x to the 4th divided by 4, and then I'll add that to this point. We don't have a x, so we have a partial x here, we have a x raised to the power 0, so I'm saying this simply will become 3y squared, which we have treated this as a constant term. Now we introduce an x at that point. Now add that to, if we integrate our cosine of x, we're saying just simply sine of x, then plus a constant c. But for this case, we won't introduce, but let's just write. Then let's perform the integral of delta n dy. Now we're saying it's the integral of 6xy plus 2. Now it's the integral of 6xy plus 2 dy. Now we are integrating these with respect to dy. So where there's a y, we'll differentiate, we'll integrate that, but where there will be an x, we won't. I will treat the x terms as a constant. Now we are saying from this point, we're having, with respect to y, we're saying 6x as a constant. Now if we differentiate if we integrate this y, we are saying we will get y squared divided by 2. Now then we'll add that to 2y. Okay, so we'll add that to 2y, so keep in mind. So now if we simplify this part, we are saying this is 3xy squared plus 2y plus a constant of integration. Now what is our potential function? So I'll write potential function, that is our original function should be, we are saying write all the terms that have appeared in both of the integrals independently or once. Okay, so our first part, we said our integral, we said this is what we got. So if we clean this a bit, we are saying this is 4, this should be x to the 4th, not 4. 4 is cancelled out, so this is x to the 4th plus 3y squared plus sine of x. Now having this part, and again having this part, we should write all these terms once only, so for us to get our potential function. So our potential function, we are writing, let's start with the x to the 4th, then added that to 3y squared, then added that to maybe let's add this. So as you can see, we have 3xy from this point, so we haven't repeated anything. So simply it's 3xy. Okay, so plus 3x, so this point, so let's check please. So let's check at this point, which we are having an x at this point. So remember, we're having an x at this point. Okay, so as you can see, we are having x to the 4th, added that to, as you can see, this term has repeated with this term, so we should write only once. Okay, so we should write only once, then add that to sine of x. Okay, so we should add that to sine of x. So we should add that to sine of x, then add that to 2y, then we'll say equal to a constant. Okay, so let me clean this a bit. We are saying this is x to the 4th added to 3y squared x plus sine of x plus 2y equals c. So this is our general solution. So if you have our initial condition, we'll say we are able to get our potential function. Okay, so we'll get our potential function if we have a general solution. So if we have our initial condition, we'll get our potential function, where the potential function has been differentiated to get these, as it has already been differentiated for with respect to x and y for us to get this derivative. So we have already gotten back to our first equation that was differentiated. Now so this is the core principle for this method, exact differential. So please like, share and subscribe to my channel, and welcome.